Okay, we're going to look at several more examples building off of the first two examples we did in this section. So we started looking at a square and a rectangle. So to remind you of what the region looks like that we're interested in, we have these sort of flat graphs here, but we've defined to let R be the region bounded by x equals y squared and x equals 9. So just to remind you what that looks like, if we're just thinking in two dimensions, is going to be the sideways parabola that looks something like this, and the vertical line through 9. So this is 9 right here. And we know that if it's x equals y squared, then when we solve for y, that tells us that y equals the positive square root of x, and the bottom half is y equals the negative square root of x. Okay, so this region in here is R that we're talking about. So for this example, and again, we're looking at finding the volume of a region using slices. For example C, the slices that we want to use are a semicircle. So that's half of a circle. And again, let's look at where this interacts with the region R. So we can see that the diameter of our semicircle is again going to be this distance between the top curve and the bottom curve. And in the previous video, we saw that if you take the top curve, square root of x, minus the bottom curve, negative square root of x, that distance is 2 times the square root of x. So if we come out here and sketch what that semicircle exactly looks like, we have a diameter of 2 square root x. This is the center of our circle. And so again, those circles are going to be going all up and down here and making sort of this half cone shape as we work our way up the parabola. So to find the area of a circle, we need to do pi times the radius squared. So if I know that the diameter is 2 times the square root of x, then that tells me that the radius, which is half of it, is just going to be 1 square root of x. So the area of our semicircle then is going to be half, because it's a semicircle, of pi times our radius squared, which means this is going to be pi over 2 times just x, because the square root of x squared is just x. So now we're ready to find our volume. Again, we're integrating from 0 to 9, pi halves times x dx. Now don't forget, pi halves is not a variable, that's a constant. So we can pull the pi halves out and kind of save that for the end, the integral from 0 to 9 of x dx. And so from here, you just need to integrate. And so if we apply the fundamental theorem, f of b minus f of a, this is what we get. And that is the volume of that figure. So this is now the third example that we've looked at where we're using the same shaped base, but we're just kind of looking at the different area formulas that we might use. Now here's another one, is using an equilateral triangle. Now you may not remember, or maybe you didn't learn in geometry, it just kind of depends, the formula for the area of an equilateral triangle. There is a formula for it, and this would be a handy one to know. And so let me give you that formula. If you have an equilateral triangle with a side of length s, then the area of that triangle, and remember what this would look like would be all 3 sides are equal to s, is the square root of 3 over 4 times s squared. Now that seems kind of random, and I'm not going to go through the derivation, but where that comes from is really your right triangle trig, knowing that this is a 60, 30, 90 triangle when you cut it in half to find the height. And so that's where that square root of 3/4 number ends up coming from. So that would be something fun for you to do while you're bored to figure out where that formula comes from. But that is the formula that we are going to use. We have already done the work and that we know that the length of this side is going to be 2 times the square root of x. So to find the volume, again, we're going to integrate from 0 to 9. And we're going to use that formula, which is going to be the square root of 3 over 4 times side squared. Well, we know that the side is 2 square root x squared dx. And I'm going to suggest that you pause this here and attempt that integral yourself. I'll give you the answer in about 3 seconds. 18 root 3 is what I get when I solve for that integral. And that's going to give us the volume of this 3-dimensional figure. And again, if you can kind of imagine what this looks like, this one is almost going to have kind of like a spine on it because all of these cross sections are going to be triangles that get progressively bigger as you work your way across. So it's almost kind of like a weird little wedge of some sort. So that's what that's going to look like. Let's look at the next one and give you some practice kind of setting this one up on your own. So if we look at E wants us to use a triangle with a height that is equal to 1/4 the length of the base. Now, let's pull this triangle out so that we can kind of set this up ourselves. And I'm going to draw this kind of wide, all right? The base is this right here. So again, we already know that this is 2 root x. We've done this several times now with that dimension. The height, they have told us, is always going to be 1/4 of the length of the base. So the length of the base is 2 square root x. If I multiply that by 1/4, we end up getting the square root of x over 2 when you simplify that down, because you get 2 over 4 when you multiply by 1/4. So now what you need to decide is what would the area of that triangle be, and then you're going to use that information to integrate from 0 to 9 and see what you get. So put the video on pause and I will show you that work in 3 seconds. If you want to check before you go too much further, the area formula that we should be using is the square root of x over 2. Area of a triangle is 1/2 base times height, which we already have defined, and then you can kind of work from there and figure out what you need. So if you want to check that, then go ahead and check your integral. Hopefully you got that the answer is 9. The trickiest part is setting up your area formula. So the next one wants a trapezoid this time with its lower base in the xy plane and its upper base equal to half the length of the lower base and a height equal to 1/4 the length of the lower base. I'm going to let you try to set this cross section up yourself. So I'll come back with the area formula in just a moment. It looks like this all simplifies down to 3x over 4. Remember, area of a trapezoid is 1/2 base 1 plus base 2 times the height. And so now we want to go ahead and find the volume. 243 over 8 should be your final answer. So there we go. These last 2 examples, we're going to go ahead and skip for now just because they're a little bit more involved than what we need to be doing. But I want to go ahead and look forward to, we're going to go ahead and pause right there for today. What I'd like to do before we finish up is to go back and look at that same example, but let's switch to using a shape that's perpendicular to the y-axis. So let's go back to here, but instead, let's use rectangles that are perpendicular to the y-axis. So I'm going to try to adjust this picture here. All right, that's not great, but it's not bad. So now let's say that we want our slices to add up this way using squares. So I don't know if you can kind of imagine what that figure would look like. When we get to the middle, that's where the squares would be the biggest, and they're going to get smaller as we work our way out. So it's going to be a shape that kind of gets taller and taller and taller and then peaks and then gets shorter and shorter and shorter, kind of like that. It's going to be kind of a weird looking shape, but that's the idea that I want to look at. So in that case, let's draw this out again. So we have the equation. This is x equals y squared, and we have the line x equals 9. This time, the side of our square is going to be this distance. Now that this is perpendicular to the y-axis, we need to do right minus left because we have to integrate dy. So the right curve is going to be 9 minus the left curve, which is the y squared. That is going to be this width right here, is 9 minus y squared. So that means every single square that we build is going to have an area of 9 minus y squared squared. So to find the volume this way, we need to first figure out what our boundary points would be here and here. So we need to set those equations equal to each other. Where does, sorry, not x squared. We have x equals 9 and x equals y squared. So that means 9 equals y squared. So y is plus or minus 3, which kind of makes sense. So this is negative 3 and this is positive 3. Okay, so we want to integrate from negative 3 to positive 3. The area, which is going to be 9 minus y squared squared dy. And from there, you can integrate that. I would probably FOIL that out and treat it like a polynomial. U substitution, it's not quite going to cut it. Or put it in your calculator. But that's how you would set that up. The main thing is figuring out which segment of the base do you need to be able to figure out your cross sections. Now we could go back to, let's look at one from, well, these graphs aren't good. Sorry, I'm going to make you sick scrolling and scrolling. We could do this here. From the 2002 exam, I only gave you part A in the area section, but part B and part C were both questions about volume. They might say, if the cross sections perpendicular to the x-axis were rectangles with a height of 3, that means that the width, this is where our rectangles would be coming out, would be right here, okay? The base of that rectangle would be the distance between these two curves. And so to find this distance, to find that area, we would have to do the top curve, which is 4 minus 2x, minus the bottom curve, which is x cubed over 1 plus x squared. Now you need a calculator for that one. But that would be how you would find the length of the base. They probably would give you a number or something for the height, and so you could figure out the area there. But this is where that idea of top curve minus bottom curve or right curve minus left curve is still playing in, even though we're talking in 3 dimensions now. So that's what you have to work on for this week, and I will see you with your questions.